All right, welcome back to CS4510 L20B. The topic is officially called Karp-Lipton theorems, but we will talk about how to apply the polynomial hierarchy. What is a polynomial hierarchy? What is the Karp-Lipton theorem? Karp-Lipton theorems interest me for two reasons. One, they require a lot of juggling of definitions. They bring in a huge amount of stuff. Two, Dick Lipton used to be a professor here, and he actually taught this class. I never really talked to him or anything, and I saw him floating around the department. I think Frederick Faulkner, he teaches 1332 now, he took 4510 with Dick Lipton, and a lot of the material was based off of his, like our final project ideas were based off of his stuff. Karp, also named Dick, was, he did the 21 NP complete problems, and he did some other stuff people are familiar with. So that's kind of the only reason I really care about the Karp-Lipton theorem, honestly. You could do anything if you wanted. In complexity theory, you could talk about anything. Before we get into that, let's talk about inside the polynomial hierarchy, and let's talk about like how to apply the polynomial hierarchy. So recall the theory of NP completeness. We have problems like clique. Clique is encodings of G comma K, where G is a graph, and G has a clique of size K. Such a problem isn't in NP. Why?
You said it is or isn't?
It is an NP. Is an element of NP. Why is it an element of NP?
Because given a witness, it's verifiable in polynomial time.
Yeah, exactly. We can even use both definitions. So the witness could be the clique, and then you just check the clique. The witness, you could also just non-deterministically guess the right clique. That's not the 3510 way to do it, but that is technically a way to do it. Yeah, what about this problem, max clique? Where it's still encodings of G comma K, but the largest clique in G is of size K. Is such a problem in NP? Why not?
You can't check all the cliques in polynomial time.
Yeah, so like we can't prove it's not an NP, but you can convince someone that there is a clique. How do you convince someone it's a maximal clique? You would have to say for all other subgraphs they're either too small or if they're bigger they're not a clique, right? So in fact, such a problem, if you had to place it in a class, what class would it be in?
P space.
It's in P space, yes. You can solve such a problem in polynomial space. Also exponential time. P space is better than exponential time. But P space may be too big, and this is the motivating definition of the polynomial hierarchy. I claim such a problem is not only in the polynomial hierarchy, but is low in the polynomial hierarchy. What are the fewest number of quantifiers, or let's say alternating swaps, you think you could use to solve such a problem?
2.
Yeah. In fact, I claim this is in sigma 2. I don't think it's in pi 2. I think it's in sigma 2. Why? We could just say G comma K is in max clique if and only if we get an exists, we get a for all, and then we get our machine, right? What should there exist? There should exist a clique of size K, right? So we'll say H1, and then we'll say for all H2, let's say, right? M of G comma K, H1, H2, right? What should M do? And let's ensure M runs in polynomial time. I'll just say M checks H1 is a subgraph of G and is a clique of size K. Then it checks if H2 is a subgraph of G, it is either smaller, as in the size of H2 ought to be less than the size of H1, or it is not a clique. Right. So if it's bigger, it better not be a clique. And so it's either smaller, or if it's bigger, it's not a clique. Right. This is sufficient for us to convince that H1 is like a witness to a maximum clique. But we need this other quantification thing here, right? So this is a problem that is said to be at the second level of the polynomial hierarchy, but not like a p-space complete problem necessarily. Think about TQBF and all the other p-space complete things we said that exist. We didn't really prove any of them, but they were like games, right? In the sense that each quantification is an alternating move, like player 1, player 2, player 1, player 2, right? Here, the input can grow, but you still only need 2 quantifiers. And the input grows is in the size of the graph. So the graph can get really big, but you still only need 2 quantifiers. You don't need a growing number of quantifiers as the size of the problem increases. So such a problem, no idea how to put it in NP, but we can say it's in sigma 2p. So this is the motivating definition for the polynomial hierarchy. The same reason we want to study that clique is in NP and SAT is in NP, we can study that max clique is in sigma 2p. Now, what is the difference between completeness inside the polynomial hierarchy, or like being in the polynomial hierarchy versus like being NP complete? There are 60,000, every time I say that number I increase it by 10,000, but there's 70,000 known NP complete problems. There's like 40 known problems like in the polynomial hierarchy that people care about, but they obviously weren't p-space complete and they obviously weren't NP complete. So this is kind of our middle-ish ground here, right? So that's where we would use that one. Are there questions on max clique, right? Why we care, why we're interested in this? So not only does each of these kind of act like a generalization of NP, I claim each level of the polynomial hierarchy has a complete problem. Not the entire polynomial hierarchy, but each level has its own complete problem, right? So there's a hard problem there, there's a hard problem there, there's a hard problem there, right? The same way SAT is NP complete and SAT complement is co-NP complete, I claim each level has a complete problem. Let Q SAT I be the subset of TQBF such that Q SAT I contains logical formula that swap between exists for all at most I swaps. And then there is some formula phi, which is a CNF, right? Such that it's true. I claim that such a problem is complete for each level, so that Q SAT I is complete for sigma I complete. To prove it's complete, we need to do 2 things. First, we need to prove that Q SAT I is in the ith level. Why is it in the ith level? Use any of the 3 definitions to prove that Q SAT I is in the ith level. Again, also, by the way, I swaps, we mean there could be more than I quantifiers here, but they'll go exists, and then when the next for all, if we change the quantifier, we call that a swap. So 100 exists and 1 for all would be 2 quantifiers, 2 swaps. Why is Q SAT I in sigma I? Yeah.
What is Q SAT I again?
Q SAT I is a subset of TQBF, where it's not just any quantified Boolean formula, but quantified Boolean formula with at most I swaps. Pop quiz, what is Q SAT 1? And also, I'll just say starts with. What is Q SAT 1?
Sigma 2.
Maybe I got an off by 1 here. But let there be 1 quantifier, and then let it only be an existential one. So exists, 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 exists. Consider TQBF formula that have no universal quantifiers. They only say exists, 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 exists. What is that problem?
NP.
Yeah, it's SAT, in fact. So obviously SAT is in NP, because you can non-deterministically guess the witness, or you can verify the witness, right? So either way, we know SAT is in NP. This is a generalization of that question. Why is QSAT I in sigma I? It's the same reason, but let's put it in words.
They have the same number of quantifier swaps.
Pick a definition of sigma I. Alternation, oracle, or logical. You're right, but let's put some meat.
Let's do logical.
Okay, logical. Sigma I then has several alternating quantifiers of existent for all. Why can you decide sigma? Why is it the case that sigma QSAT I has such a logical definition? You could just say the quantifiers match up, so that's kind of like the answer. If I were to say the alternating definition, for example, I would say non-deterministically guess the first few quantifiers, and then universally guess, and then the same reason AP was a subset of P space, we can in fact put restricted TQBF. We put TQBF in AP, right? We can put restricted TQBF in restricted AP. Same idea, right? Okay. Now we need to prove it's sort of sigma I hard. That means for all L in sigma I, there's a polynomial time reduction to QSAT I. Why is that true? This is a difficult proof, but you can make it simple by some magic words. Yeah. Cook-Levin. So Cook-Levin, recall in Cook-Levin, we spent a lot of time on the Cook-Levin theorem, so we understood the proof intimately, so we don't have to repeat it all the time. For Cook-Levin, recall we proved that for all A and NP, there's a polynomial time reduction from A to SAT, in the sense that we converted the machine, the NP machine, or the verifier machine, into a CNF, right? Just do the same thing. It would be a lot of programming, and I don't want to get into it, but it's definitely possible. It's totally fine to do. I mean, what you would normally say here is by a similar construction to the Cook-Levin theorem. I could do all this programming. Don't make me, I'm not going to, but I could do it. And you do that to the alternating polynomial time machine. So the satisfying assignment, quote unquote, would be literally the alternating quantifiers here, right? When the machine makes existential, universal, existential jumps, you have a TQBF with existential, universal, existential. Same thing. Okay? So every level of the polynomial hierarchy has a complete problem. Fine. In fact, I'm 99% sure, I didn't double check it though, that max clique is complete for sigma 2. Right? Similarly, pi I also has a complete problem, the same way SAT complement is complete for co-NP. Okay? So every level of the polynomial hierarchy has a complete problem. Questions on that? Okay. So is it a real hierarchy or not? That's the next question we'll answer. If the polynomial hierarchy is infinite, in the sense that it is real, is an open question. But we do know that it is heavily influenced by perturbance. If I were to draw it again, we put P here, which is sigma 0, which is equal to sigma 1. No, excuse me, pi 1. And then from there, we generalize to get sigma 1, sigma 2, sigma 3, sigma 4, and so on, right? Pi 1, pi 2, pi 3, pi 4. Let's just draw our arrows. Here's the claim I'm going to make. Let's just leave it there for a second. If there is an I such that sigma I p is equal to pi I p, then the polynomial hierarchy collapses to sigma I p equal pi I p. So what this means is if there's a single level of the polynomial hierarchy that's closed under a complement, maybe let's say after level 100, the polynomial hierarchy is closed under a complement. If there is some situation like this, then what we say is that it collapses. If at any moment a left stick is equal to a right stick, this whole portion does not exist anymore, and the whole thing stops here. The polynomial hierarchy collapses, in fact, to that level. Okay? So basically, it's a set of struts, and if you remove or break any strut, the whole thing will fall over. We'll prove that in two ways, but this is the first one we'll do. Okay? If there's a single level, even 1,000, 10,000, if it ever stops, not even if it stops, but if any two levels are equal, then the whole thing falls over just to that level. Let's prove it. Suppose for some I, sig pi ip is equal to sigma ip. Consider sigma I plus 1, using the quantifier definition, was an existential generalization of what? Right? I think I didn't erase it. So what goes here? Pi I p, correct. It's an existential generalization of the previous class. You can take pi 2p and get sigma 3 by existentially generalizing it, right? But if we know that pi ip equals sigma ip, what do we know about pi ip?
It's equal to sigma ip.
Yeah, so this is just exists sigma ip, which is what?
Sigma p I plus 1.
Almost. This isn't. Sorry?
Pi.
Simpler. What is. Here, I'll write it out. Sigma I exists what? It exists pi I minus 1p, right? Exists is what? Yeah. So this is in fact just exists pi I minus 1p, which is just sigma ip. What I'm saying is here, this is a sigma, this is an exist, that doesn't do anything, that doesn't generalize. So compress that quantifier like we did previously, right? So in fact, what we've proven here is that pi I plus 1p is equal to sigma ip. So the next level is not on top of it, it actually just falls down to that level. What about any other level? What about for k exceeding I, we have sigma k is equal to exists for all, call that, I don't know, for all exists pi I p, call this k minus I, right? This is just then exists for all exists, sigma ip, right? And again, here we have k minus I quantifiers. But it exists in a sigma, so we can compress those. So we get exists for all sigma I, sigma I k minus I minus 1, right? What do we know about sigma I? It's pi I. So swap, compress, swap, compress, swap, compress, swap, compress. Chain this down, this will just be sigma ip, right? So you can repeatedly swap those around, compress quantifier, swap around to get sigma k for any level above into sigma I. Therefore, the entire polynomial hierarchy collapses to sigma I p. If for any level sigma I equals pi I. Done. What is this really here? This is just a generalization of the argument of what happens if NP is closed under complement. Bad things happen if NP is closed under complement. This is one such example. Okay? Right. Now, what if the two levels are not equal to each other? What if they are just any two levels? It turns out we get a similar problem. If any two levels are equal, then the polynomial hierarchy collapses. I will prove a simpler version of this, which is let's remove this specific strut here, right? So if we remove this strut here, I claim the whole thing should break, right? Kind of, I mean, when you look at the picture, it's kind of obvious that's what's going to happen, but let's prove it. I claim that if P is equal to NP, that implies that pH should be equal to what? If you had to guess. And simpler. Fall down. Fall or down, more down. Yeah, it's P. Right. So, like, if P equals NP, what do you know about co-NP? Yeah, P is co-P. So if P equals NP, co-P is co-NP, which is P. So, in fact, there is no co-NP if P equals NP. Co-NP only is there when we assume NP is not closer to complement. So that it is something different worthy of study. Otherwise, it's just all P, right? Similarly, if P equals NP, we generalize that countably infinitely many times such that this whole thing is equal to P, right? Let's just formalize this. If P is equal to NP, we know that co-P is equal to co-NP, right? That's just definitions of things. But what is co-P? Yeah. And by assumption, we know that implies that co-NP is equal to NP, basic set stuff, right? If P equals NP and P is equal to co-NP, then co-NP equals NP. What do we know must be true by the previous theorem? This is really pi 1, and this is really sigma 1, right? So what we know is that if pi 1 equals sigma 1, then the polynomial hierarchy collapses to that level. The polynomial hierarchy collapses to NP. But by assumption, NP is just P. So done. In fact, if P equals NP, there is no polynomial hierarchy. It's not worthy of study. The whole thing falls down to just this level, so, right? It's all gone, right? All of the problems are there. So if P equals NP, not only is clique in P, max clique is also in P, right? So problems in the polynomial hierarchy that they're also in P space, but are in also somewhere smaller. A problem like max clique would also be in P for the same reason that clique, for a slightly more complex reason, that clique would be in P if P equals NP, right? So we add this to mounting evidence that, like, so when I was studying complexity theory, I didn't really understand why P does not equal NP. Like, why does everyone just, like, if you poll people right now, 99 to 1 people will say P does not equal NP. I didn't really understand why. There are 10,000 little theorems that imply this. So you kind of have to have a body of knowledge. And this is one of the reasons. We don't expect the polynomial hierarchy to collapse. That doesn't make any sense. For that reason, we don't expect P to equal NP. Because if it did collapse, then all this would also be in P, which doesn't make sense. You may object maybe 80-20 to clique not being in P. But max clique not being in P sounds harder than clique, yet if P equals NP, then both of these would be in P. Kind of, it's harder to sell that, you know. It's all heuristics. Okay, I mentioned that applying the polynomial hierarchy is pretty simple, and these are the kind of arguments we get to make. We just got to get to throw stuff around. Does the polynomial hierarchy have a complete problem? The polynomial hierarchy has a complete problem if and only if the polynomial hierarchy collapses. So kind of strange on that. What do we mean by a complete problem? We proved each level of the polynomial hierarchy has a complete problem. I claim if the entire hierarchy has a complete problem, then the hierarchy collapses, okay? we don't expect it to collapse, so we don't think there's a complete problem. Suppose that pH has a complete problem. Suppose there is some A such that it's complete for the polynomial hierarchy. What does that mean? A would be in the polynomial hierarchy, and for all L in the polynomial hierarchy, there's a polynomial time reduction from L to A. Right? Same definition as a p-space complete problem, as an NP complete problem, whatever. Fine. Suppose such a problem exists. Since A is in the polynomial hierarchy, there exists some K such that A is an element of sigma K. Right? And since we may reduce from all L in polynomial hierarchy, we have a polynomial time reduction from L to A. Each level being closed under complement implies that L is also in sigma K. But that's sufficient to put the entire polynomial hierarchy in sigma K, implying collapse. Right? If it's complete for the polynomial time hierarchy, it's in the polynomial hierarchy, so the whole polynomial hierarchy can be reduced to that level. That's kind of the idea, right? In fact, there is a polynomial hierarchy hard problem, but not a polynomial hierarchy complete problem. What is a problem that is hard, pH hard? Yep. Yeah. Everything reduces to it, but in a way that's a special case and never fully general. So, kind of strange. Let's do the other way. Suppose the pH collapses. Why does it have a complete problem? Yeah.
Because it has a highest level, and there's a highest level, and every level has a complete problem. The complete problem for the highest level would be complete for all.
Perfect. Suppose pH collapses to, say, sigma K, P. Then QSAT K is complete for pH. QED, done. See how easy that was? Okay. Where does the polynomial hierarchy fit in? So we have P, NP, co-NP, and we have accountably infinitely many generalizations of that. That is the definition of the polynomial hierarchy, right? What is the upper bound of the polynomial hierarchy? Name some class bigger than pH. Anything, yeah.
P-space?
Yeah, P-space. There's one more thing bigger than P-space is exp, right? Just for artistic license, let's put that there. Should pH equal P-space? Why not? We have infinitely many classes here. P-space is one class. This is infinitely many classes here. pH equals P-space. Ironically, in kind of like an Icarus myth kind of way, the bigger the hierarchy is, it will falter. I claim if pH equals P-space, that implies the polynomial hierarchy collapses. Why is that true? One sentence. Yeah.
P-space is the top. There's a top level.
So P-space definitely contains pH. It is a level. But I claim if the level is met, it collapses. Ironically, we think it to be infinite, but in a bounded way because it's all still decidable within P-space.
There's P-space complete problems.
Okay. So if pH equals P-space, what do you know must be true?
There's pH complete problems.
And then, yeah. If pH equals p space, then TQBF is pH complete, implying collapse. So if it was big enough to be p space, it would collapse. But we don't think it should collapse. Therefore, we don't think modus tollens here, pH is equal to p space. We think it to be strictly so. We know that there's p space complete problems here, and we have pretty good reason to believe that pH is strictly contained in p space. Is there a middle area here? Yeah, and it's kind of difficult to prove that. It's like a generalization of Leibniz's theorem where NP intermediate exists, right? We have P, NP complete, there's a middle area. We think a middle area also exists here. Nothing interesting, I think, exists here, though. But you can show that it's not empty, assuming that pH is not p space. Either way, we know a lot about the polynomial hierarchy because it sits in a very nice area for us, right? It sits between NP and p space, and we don't suspect it to collapse. We have strong belief, for the same reason NP does not equal co-NP, we have much stronger belief that sigma 10 does not equal pi 10, and so on. Right? We don't expect any relationship there to be found. So for that reason, it's useful in separation of things like this. Right? In fact, I'll tell you, as a quick aside, we know that subgraph isomorphism is NP complete, right? I proved this in 3510. I don't know if you guys remember that. But subgraph isomorphism is given two graphs as one a subgraph of the other, right? Graph isomorphism is, we don't know. I mean, this is an open question if it's NP complete or not. But we know if graph isomorphism is NP complete, that implies that the polynomial hierarchy collapses. So we take that as evidence, but not proof, that graph isomorphism, as in the sense that not the case that one is a subgraph of the other, but a graph is equal to the other. We take this as evidence that graph isomorphism is probably not NP complete, because if it was, bad things happen. And we don't think bad things should happen, so the hypothesis is probably not true. Right? We can use this, the collapse of the polynomial hierarchy, and its unlikeliness to prove many things. And that's sort of what Karp-Lipton will segue us into. Questions on this? How to use the hierarchy, kind of? The proof of Karp-Lipton is relatively simple, but the statement is what is difficult about it. It only takes like 6 minutes to prove, but to understand what it says is the only reason, really, we define the polynomial hierarchy. So the question, it was thought at the time, it was conjectured by many people that you could not compare non-uniform complexity classes and uniform complexity classes. For example, I put P here, and then I put NP here, and then I put co-NP here, and then I put P space here, let's say. Okay? Recall the class P/poly. It's a non-uniform class, polynomial advice machines. That's less interesting than the circuit definition, which is polynomial sized circuit families, right? Where should P/poly go on this chart if we had to draw it? This is a difficult question. Is P/poly contained in P space? What did we prove last time about P/poly? It's been a minute.
Is it equal to p space?
Nope. It's sort of a circuit version of P. At least that's what we would like to think. But it unfortunately contains undecidable languages by the definition. All of these are subsets of the decidable languages. If it halts in polynomial space, it always halts. So it's never undecidable, right? So unfortunately, if we were to draw P/poly, it would look something like this. Okay. It just is not good to put on your diagram. So most people ignore it. It's something way over there. past, the Turing decidable problems, the halting problem is in P/poly, unary version of it, so on. So it doesn't make it's not nice. So for a long time, people conjectured like, okay, we draw the uniform complexity classes on this diagram, and then the non-uniform complexity classes we could draw on this other diagram. And there is no relation between the two, and we cannot conjoin ideas. But the Karp-Lipton theorem, the significance of it is that it did. All it says is that if NP is contained in P/poly, that implies that the polynomial hierarchy collapses. What does this mean? It was thought, so relativization came out, there's coping mechanisms. Maybe SAT can be well approximated. We know this not to be true. You cannot approximate SAT too well. Maybe there's a randomized algorithm for SAT, and it's not actually hard. We also don't think this to be true because now we believe P equal BPP. SAT was thought, maybe it's tractable in the sense that maybe there's no polynomial time algorithm, fine. But there could be a quadratic sized circuit for SAT in some sense. This proves if there is a quadratic sized circuit for SAT, bad things should happen. So there better not be. That's all this really says. What we'll explicitly prove is if SAT is in P/poly, then that implies that pi2 is contained in sigma 2. This is enough to imply collapse, it turns out. So that's the restricted version of that. It's like this connects uniform complexity classes with non-uniform ones, and that's kind of the significance of it. Okay? Before we get to there, let's discuss the consequences of what happens if SAT has a polynomial sized circuit. Right? So let's suppose that SAT is in P/poly. If SAT is in P/poly, then there's a polynomial sized circuit family, C, which is like, let's say C0, C1. These are, remember, a circuit family has infinitely many circuits. When you want to run an input of length n, you pick the nth circuit. It has n input wires. That way you get around the problem of having a 32-bit adder trying to add 60-bit numbers or something, right? You just pick the 60-bit adder instead. Such a circuit, if this is true, is a polynomial size and takes on an input of phi and outputs a 0 or a 1, right? Something like this. It solves the decision version of SAT in the sense that it always tells you if this formula is satisfiable or not. And let's say it's polynomial size. I claim that if there exists a decision circuit for SAT, there exists a search circuit for SAT, C prime, such that C prime on phi outputs the actual satisfying assignment. It actually outputs n bits such that when you plug those into phi, it outputs a 1. Right? Why is that true? What I'm saying is if there exists a polynomial sized circuit family for the decision problem, why does there exist a polynomial sized circuit family for the search problem that actually outputs the assignment? Why is that true? Yeah.
In order for the decision version to know if it's satisfiable or not, it has to come across the satisfiable assignment.
That is like the best engineering answer you could give. So like intuitively, if it solves the decision problem, somehow in the wires it must solve the the search problem, and just wire those outputs correctly, right? That's like a small polynomial size modification. But we can't assume that. What if the polynomial size circuit family for SAT does like a Fourier transform, and then like like does a quantum simulation, and then like somehow this answer is outputted and we don't know how or why. There is an algorithm problem that and the lecture's on YouTube now, but it basically taking the determinant of this funny matrix outputs the number of minimum spanning trees. But it doesn't actually tell you what the minimum spanning trees are. It just tells you the number of them. So such strange theorems can exist. So maybe there's a way it solves the search problem, a decision problem for SAT, but not the search problem, perhaps. I still claim there's another way we can do it, even if we don't know this. Yeah.
Are oracles relate to this, or is that?
Yeah, I mean, actually, like when we do this in the algorithms, this is just a circuit version of a 3510 thing, which is that the decision problem is in P if and only if the search problem is in P. You can think of C prime having oracle access to C in the sense that it has copies of it, rather than an oracle necessarily. C prime is in fact just going to be made up of copies of it. For example, here's how C prime is going to work. If phi is in SAT, you know it's satisfiable, right? But you don't know what the satisfying assignment is. So then you ask two separate questions. Is phi and x1 in SAT? And is phi and not x1 in SAT? If phi and x1 is in SAT, what do you know must be true? If phi is in SAT and phi and x1 is in SAT, what must be true? Where this is a clause of size 1, let's say.
X1 is true.
Yeah. This implies x1 is true. This implies x1 is false. So what you do is you have the size of C prime is approximately 2n times the size of C plus some constant. Right? Essentially, what this is binary search over the 2 to the n size truth table. You check x1 and then you go up or down. You check x2, you go up or down, and so on. So it's actually binary search over the 2 to the n size truth table, which should take n steps. So that, if C is polynomial size, then so is C prime. First lemma, if SAT is in P/poly, there's a circuit family with n output wires instead of just one output wire, but the circuit family outputs the satisfying assignment itself. That's our first lemma. We need that for Karp-Lipton. Questions so far? So assuming that such a circuit family exists and is of polynomial size, we want to prove that pi 2 is contained in sigma 2. So what we can do is we want to prove now that if SAT is in P/poly, again, that implies that pi 2 P is contained in sigma 2P. So let L be in pi 2P. That means that W is in L if and only if for all x there exists a y such that M W x comma y accepts, right? Now, how can we use the polynomial size circuit family here to modify this? We know that by the Cook-Levin theorem, we can convert the machine M into a CNF, right? So, by Cook-Levin, we can convert M, W, and X into some CNF phi M comma W comma X, right? Now, what should the satisfying assignment to this CNF be?
What?
Yeah. In fact, Y is the existential part of the assignment. So the satisfying assignment to this CNF ought to be Y. So what that means is C prime for some K on input phi M comma W comma X should output what?
Y.
Yeah. If this is a circuit that solves SAT in polynomial size, we don't need the polynomial size part, but this is a circuit that searches for a CNF, right? It searches the satisfying assignment for a CNF. So what we can do is something called witness extraction. We convert a machine to a CNF via Cook-Levin, and then we say, what was the satisfying assignment to this? And then we use the circuit to get that satisfying assignment, okay? Next, we can do a thing called self-reducibility, which is instead of quantifying over Y, we just compute Y. For all x, we don't need Y anymore, because we can find Y using the circuit. for all x, m on w x ck prime phi of m comma w comma x. Okay? So instead of y having to be non-deterministically guessed or quantified over, the machine will just take the circuit, simulate it on the CNF that is reduced from it. So this is called self-reducibility. You take the machine and you ask it a question about its own CNF. And instead of y, it can ask about this. Now, this is not the exact same m. There's a slight modification there for it to actually get the answer from the circuit. It wires it slightly differently, but it's almost identical, right? Whenever it would use y, it would use the output of this circuit, right? This is almost right, right? There's a problem, though, is we don't know what the circuit is. We don't know how to get the circuit. We don't have the circuit. If m was hard-coded with the circuit preemptively, we would know this. But we can't do that. How can we obtain the circuit? Yeah.
Another search circuit?
We could obtain the circuit through another search. The circuit ck prime, k is just some parameter of the circuit family, solves SAT in polynomial time. Nah, let's not say that. I claim there's a way to get ck prime. This machine needs access to that circuit, but it doesn't have it. How can it get access to that circuit?
As it there exists.
Yeah, just guess it. Use non-determinism to guess the circuit. Okay, so just guess the circuit and then use that to perform witness extraction on myself, and then now I don't have to quantify over that. Since it's very important here, when you do the polynomial hierarchy, you must quantify only over polynomial-sized strings. So here, this only can work because we assume that the circuit is polynomial size. Because the circuit is polynomial size, we can guess it. Non-deterministically polynomial time, guess the circuit, then for all x, we continue the simulation. This is an exists for all statement. So up to the logical definition, this tells you that L is an element of what?
Sigma 2? Or
Yeah, no, exactly, sigma 2. So that implies that pi 2 is a subset of sigma 2, which implies collapse. QED. Pretty funny how you can just guess the circuit and that makes all the problems go away. Questions on that? I'll do two more proofs like this. After this came out, there was basically a Cambrian explosion of like, how could you use this technique of self-reducibility? How could you use this technique of guessing circuits that you assume must exist to prove many things? So the original paper ended up getting, by the time it made it to publication, there was basically 10 theorems in it of this form. Let's see if I get the next one. If exponential time has polynomial-sized circuits, then that implies that exponential time is contained in sigma 2. Right. So we want to prove that if exponential time has polynomial-sized circuits, then all of exp, including p-space, is contained in the second level of the hierarchy. This includes ph, p-space, whatever, right? If L is in exp, what do we know about it? There's a machine such that W is in L if and only if M on W accepts in 2 to the n to the k steps, right? So there's a sequence of configurations of M, C0, Z1, all the way to, say, Z2 to the n to the k, right? So those configurations exist for this machine, if it accepts, right? But if XP, exponential time, has polynomial-sized circuits, what that we can say is that there's a polynomial-sized circuit family such that C of I will output the ith configuration. That is a bold claim, a bold statement, but it's okay. I mean, it's fine. How many input wires should such a circuit have?
Would it be 2 to the n to the k?
It would need up to 2 to the n to the k inputs, but I think you can get away with, in binary, n to the k. So you would only need, it's still polynomial size, right? The exponential thing doesn't hurt here. The core idea here is that you can determine if the machine accepts, not by actually running the machine, but just by syntactically checking some of these configurations. If you can syntactically check these configurations, the first is initial, the last one is accepting, zi plus 1 follows from zi, basic syntax checks, then you can actually determine if the machine accepts. So what you could do instead is say w is an L, not if the exponential time machine accepts, but if there exists a machine, let's call it a simple checker T, that takes as input w, but then also z0 to zk, z2 to the n to the k, and it's somehow able to check those. And if it can check those, it's like, yeah, this is the computation history of the machine that should accept. I can do so efficiently. The problem is it doesn't have access to such configurations. So what we do is we can just start throwing quantifiers there, right? So what we could do is say this is true for all, if for all I, t prime of w c, comma ci accepts, where t prime now simulates the circuit universally on all I, right? This is, the t prime here is slightly modified from the t because now it just says, no matter what I you give me, I'll check it's a valid configuration, okay? But how do we get the circuit C? We need to have access to a polynomial size circuit family for exponential time. How can we gain access to such a polynomial size circuit family? It's the same answer as the previous one, I'll tell you that.
I remember what I said.
Oh, okay.
What it was.
Just non-deterministically guess the circuit. Just guess, yeah, there you go. So we say W, this is not complete. We can say W is an L if and only if we can guess this circuit C for all I, T prime on W comma Ci. Accepts, right? Now, Meyer's theorem, in contrast to the Karp-Lipton theorem, actually has a very important corollary. So, in complexity theory, I gave this big, like, hoo-ah that lower bounds are hard to prove. Upper bounds are easy to prove. Why are upper bounds easy to prove? All you have to do is, to prove an upper bound, all you have to do is like give the big O, right? You just like give an algorithm for it, you solve it. Easy. Proving a lower bound is difficult because you have to show for every possible algorithm, aka Turing machine, every single algorithm that solves a problem correctly must take a minimum number of steps. That for all part makes it kind of difficult and cumbersome to work with. But Meyer's theorem here can be used to link upper bounds and lower bounds and kind of imply that actually lower bounds may not be that hard. If p equals np, specifically if np is contained in p, that implies that exp is not contained in p slash poly. What is this here? P is a subset, np is a subset of p, is a polytime upper bound on np. So this is an, if you can prove this, this is an upper bound, right? Just give a polytime algorithm for SAT, right? The xp not in p slash poly is a poly-sized circuit lower bound on exp. Right? So a upper bound can in fact imply a lower bound. Let's prove this in a second. Suppose P equals NP, but X is contained in P/poly. If X is contained in P/poly, what do you know must be true by the previous theorem?
pH collapses.
Yeah. pH is in fact collapsing to sigma 2. But what do we know about sigma 2? Sigma 2 is contained in pH. Wait, did I get this right? Let's see. Sorry, specifically, EXP collapses here. There we go. EXP collapses to sigma 2. But sigma 2 is contained in pH, right? And what did we say last time happens if P equals NP?
pH collapses.
To what level?
The base level.
P. Yes. What's the contradiction?
EXP contains P.
Yes. So EXP contains P, is contained in P, contradicts the time hierarchy theorem. We know P is a strict subset of EXP, right? EXP being contained in P contradicts the time hierarchy theorem. So obviously, this is sufficient for us to prove that an upper bound implies a circuit lower bound. This is the sort of moral of Meyer's theorem, right? Questions on this one?
What was the name of this theorem?
Meyer. It's named after Albert Meyer. Okay, I'll give you one more. Then we can take a break. For each K, this is due to Ravi Kannan. I think he stopped working in complexity theory in the 80s and switched to data science, but he proves that for every K, there exists an LK such that LK is in sigma 2 and LK is not an element of size n to the k. So he gives a language that's in, this is NP to the SAT. It's not super high in the hierarchy, but he claims that for each K there's a language that cannot be decided by size n to the k circuits. Now note that this is for each K, but this is not saying anything about pH versus p-poly. That doesn't say anything at all, right? Because it could be the case that LK is in size n to the 2k. Like, it doesn't prevent that at all. So the fact that, for example, quadratic time is a subset of cubic time does not imply p does not equal p, but in fact that for each k, he can construct a language that has a circuit lower bound on k. This is Kannan's theorem. So first, we'll prove LK, we'll warm up. We'll give some LK to be in sigma 4. Okay. The way we'll do so is define an alternating Turing machine that uses at most 4 steps. So here is the definition of such a machine. Before we do so, any questions on what we're about to prove? Yeah.
LK in sigma 2. What is LK just a language? I mean.
Yes. Is it useful? No. Yes, it's not like TQBF or SAT where it's like, that makes sense. We want something interesting. And in fact, the point of this proof is that remarking on the proof is very strange. That's kind of why I'm interested in presenting it. I'll show you the machine. By the way, this is also sigma 4, not sigma 2. So we'll do sigma 4 first and describe how to improve it. So sigma 4. So the machine is going to do it's the sigma 4 machine is going to behave as follows. On input W, first it's going to guess a circuit, C star, of size n to the 2k plus 5, which he earlier proves like that's big enough for this to work out. Don't worry about those numbers specifically, right? Then he's going to make a universal jump, C prime here, for all C prime of size n to the k plus 1. There should exist some y of size n such that C star of y does not equal C prime of y. By the way, what is this machine going to accept or reject? It's going to guess the C star and then accept if the guessed circuit accepts. So that's what its actual accepting and rejecting behavior is. I haven't finished the machine description so far. What does it do? There's a name for this. We've actually seen this technique before. Yeah. This is diagonalization. What you're going to do, non-deterministically guess a circuit such that you co-non-deterministically guess all the other circuits and make sure that you're different than each circuit on at least one string. Here, for all other circuits that are smaller, you ensure all of them are wrong on some string. So you guess some circuit that is different than every smaller circuit. That's diagonalization. So here, you can construct this language by diagonalization. There is a slight bug, which this would be a sigma 3 machine if we stopped here, but you can improve this to sigma 3, but we need to finish this. And the problem is that when you have an input of the same length, you might guess a different circuit. So what you need to do is just make sure that every time you run on, let's say, 0, 0, 0, and then 0, 0, 1, you don't guess different circuits. So you just need to enforce that you always guess the same circuit. So the way we'll do that is that we say, at this step here, for all C of size less than or equal to C star, whatever that happens to be, there should exist some C naught of size n to the k plus 1, such that C0, and then for all Z of size n, we're going to say C0 of Z must equal C star. There's no C of Z. There we go. Right? So all this really does is, you don't even have to read this. This is just baggage. It just forces you, baggage. It just forces, whatever. It forces you to, for the simulation to work correctly. This part is the important diagonalization, right? So we know that this is some LK. LK here is in sigma 4p because we gave the machine for it. It runs in polynomial time. We also know that because it diagonalizes against all smaller circuits, it's not in that language. So we know that LK is also not an element of size n to the k. Good. So we know that some language is in sigma 4 and does not have n to the k size circuits. Okay? Now, how can we improve this to sigma 2? How can we prove some language in sigma 2 does not have size n to the k circuits? Recall that we just proved that LK is in sigma 4p and LK is not in size n to the k. I claim, here's the claim. There exists an L such that L is in sigma 2p and L is not in size n to the k. Okay? We can improve this to sigma 2. Here's how we're going to do it. Case 1. SAT has polynomial size circuits. Case 2, it doesn't. One of those must be true. So our cases are total. Agree? If SAT has polynomial size circuits, what must be true? What did Karp-Lipton tell us?
H collapses.
To what level?
Base level.
Not quite. We went for all exists to exist for all. We can only collapse to the second level.
Sigma 2.
Yeah, I think it's open if you can collapse it further. We're pretty certain it's around there. Maybe a little bit less, but like not to NP, I think. By Karp-Lipton, sigma 4p is then contained in sigma 2p, right? So LK is now in sigma 2p, but LK is still not in size n to the k. Somehow, if SAT has polynomial size circuits, you can improve this machine, somehow simulate it on a sigma 2 machine. Don't know how. But if you had polynomial size circuits for SAT, you could do it. We don't know how to do it, though. So this would be in L sigma 2, and it's still not in n to the k size circuits. Fine. What happens if SAT is not in p/poly? If SAT is not in p/poly, then SAT doesn't have a polynomial size circuit, so it definitely doesn't have a size n to the k circuit, right? So almost trivially, SAT is not in size n to the k. So either L is equal to LK or SAT. One of those must be true, and one of those is in sigma 2 and not in size n to the k. We don't know which one. So the proof is non-constructive, and this is what complexity theorists call results, because it's kind of a joke. We proved a circuit lower bound, but do we know on what? We don't know what we proved the circuit lower bound on, but we did prove a circuit lower bound. So this is kind of the cope that people do. They're like, yeah, we've proved some language in NP to the NP cannot be decided in polynomial size circuits, but we don't know which one. And in fact, if you just assume P does not equal NP, then this proof is trivially, it's just case 2, it's SAT, right? We have not really proven a lower bound on any specific problem, yet we would call such a thing a lower bound, because that's kind of like, every proof in complexity theory at the higher level that claims something kind of looks like this, where it's sort of, you could call this analysis win-win, where you reach the theorem for totally different reasons. Either it's SAT is in p/poly and it's true, and congratulations, I mean you assumed that anyway. Or if it's false, you reach the theorem, the main thesis, through a more cumbersome and complicated mean. But since you don't know which case it is, you don't really show anything applicable. So such a theorem is kind of useless. But because the P versus NP question is so hard, this is kind of the best you can do. We don't know how to do anything else. So, question on Canon's theorem? Okay, let's take a break.